Sure, talk. What do you think?
Sure. It was. What was it? You want to leave that on, Christian? Leave that on so you. This one on? Yeah. Okay. Yeah.
Yeah. Otherwise, it's a bit dark
Okay.
for people seeing you on Zoom.
Oh, I see. I see. So I can maybe call you.
And also, before we get started, for everybody in Zoom land, we're going to ask you to mute yourselves.
A few more minutes.
Doug should be coming. Yeah. What I thought this is one of it. Well, suppose we might as well get started. Okay, so excellent. So thank you all for coming to Christian's dissertation defense. I'm Michael Connolly. I'm with Bo, I'm one of his advisors. At the start, there's a few people I want to thank. First and foremost, I want to thank Karina for being basically willing to let us have Christian for a couple of years, and for being so helpful and supportive of Christian. And I want to also acknowledge Christian's mom, who came all the way from Chile to be here today. And of course, I need to thank Christian for being such an awesome student. Couldn't really hope to have a better student. He only really made two major mistakes. First of all, he's better dressed than I am. And second, he enabled his advisors and his wife to collaborate against him in the creation of this slideshow. So as he said, we'll start at the beginning. Like any great student, he showed great promise at an early age. So he grew up in Santiago in Chile, then came here to Hawaii to join us to pursue a degree in astronomy. Of course, in Hawaii, there's lots of, you can go hiking and swimming at the beach and more swimming at the beach. And also, of course, along the way, you meet lots of new people and make new friends. And one thing that might not be known to most of you is that Christian is actually quite an excellent dancer. And not only is he an excellent dancer, he's also an excellent dance teacher. So back in normal times, our conversations in my office would often oscillate between astrophysics and how we run our dance classes. But of course, he came here to do a degree in astronomy. And at the beginning, he didn't quite have it down how you're supposed to do it. But then as time went on, he got better. See, by this point, he learned how to use a tripod, which is excellent progress for a student. But a degree in astrophysics takes lots of sweat and hard work, which it did. But now he's finished. Now we're here at his dissertation. and he's about to go off to take a postdoc at AZA in Taiwan. So we're really happy that he's finished. Unfortunately for you, the slideshow is not finished. So the last slide, I'll leave you with this picture, and I'd like to present to Christian.
All right. Thank you, Mike, for that wonderful presentation. I really appreciate it, and also my wife for lending him all these nice pictures of me. It was really cool to see. Okay, let's see. All right, so thank you everyone for being today here, for attending in person, and for everyone who's watching this online. My advisors are Michael Connolly and Bo Rypert, and my thesis committee members are Greg Dobman, Sasha Krot, and Sudong Sun. Today I'm gonna tell you about the evolution of magnetic fields in low mass young stars. So I'll start by telling you that by observing the sun, we have learned that there is a deep connection between the stellar internal structures of the sun and stars and their magnetic fields. The sun, it's a main sequence star, and its interior, it's composed of a radiative interior, 70% of it in radius, and the 30% outer layers are convective. Now, we think that the sun produces its magnetic field in a combination of two things mostly. It's the convection of the outer parts and also the rotation of the star. More importantly, the differential rotation in the core. This magnetic field is known as a dynamo, so it's going to generate itself and it's going to produce all the aspects we see in the sun, all the solar magnetism, winds and spots, and all the solar activity. And the interface between the radiation part and the convection of the star, known as the tachocline, it's thought to produce actually a very important role in the evolution, in the development of these magnetic fields. Now, despite we have learned a lot about the solar magnetic field, we must admit that what we observe in the sun is just a very brief moment in the life of a star. If you want to understand what happened in higher mass stars and lower mass stars, we need to look at what happened with their internal structures and how their magnetic fields are different. Stars that are significantly more massive than the sun, maybe 1.5 or 2 solar masses, are going to have a fully radiative interior. These are going to have actually very weak magnetic fields, often non-detected. And when we do detect them, it's only in about 5 or 10% of these stars. Just for comparison, I'm going to tell you that the magnetic field strength we measure on Earth with a compass is about 0.1 Gauss. That's about something we cannot detect for a star. For stars with masses between half a solar mass and 1.5 solar masses, we know stars are going to have a small radiative core and then convective envelopes. And these stars could have magnetic field strength between 10 and about 100 Gauss on average in their surface. 10 Gauss is about the average of the sun, and 100 Gauss or a few hundred Gauss, that's the strength of a fridge magnetic field. Then we have the lower mass stars in the main sequence, which are going to be fully convective. This is about half a solar mass. And these stars have actually quite impressively large magnetic fields, 1,000 Gauss or 2,000 or 3,000 Gauss. This is about the magnetic field strength we see in sunspots, these very dark regions in the sun. Now, it's actually quite interesting that these stars produce stronger magnetic fields, especially since then they don't have this tachocline, this interface between the radiative part and the outer convective part that we see in the sun. It's actually, there's no consensus right now why or how these stars can produce such large magnetic fields. Now, we can learn about the connection between stellar internal structure and magnetic fields and dynamo process by studying young stars. Why young stars? Because something these three type of categories of stars share in common is that when they were born, they were all fully convective. all stars less massive than 2 solar mass are going to be born fully convective. And therefore, this differentiation in the internal structure is going to happen during the pre-main sequence, during the first few 100 million years old, as they evolve towards the main sequence. So what we know about magnetic fields is that T Tauri stars, these very young, fully convective stars that have ages of only a few million years old, are going to have strong magnetic fields. And the next thing we know is that in the main sequence, stars will have not only different internal structures, but also different magnetic field strength. What we don't know is what happens in between. So one of my goals, the goal of my thesis, is to fill in the gap here and try to connect empirically what's the measurements of the magnetic fields in stars and this evolution of the stars, how they change their rotation and how they change their internal structures. Here, there might be the key for understanding not only or better understanding the solar dynamo and the magnetic fields in the sun, but also understanding how magnetic fields are generated in stars with completely different stellar interiors. So in pre-main sequencers, in young stars, in T Tauri stars, we know the magnetic field has a very important role. We know it's going to be the link between the star and the circumstellar material. Gas is going to flow from the gas onto the stars through these magnetic field lines in a process called magnetospheric accretion. And the angular momentum is going to go the other way around. These magnetic fields allow the star to release some of the angular momentum. And therefore, the star is going to spin down. If there were no magnetic fields in these stars, they will rotate so fast, they will actually break up. Another way the stars have of getting rid of angular momentum is through powerful jets that we observe in the early stages of evolution of a star. And these are also a phenomenon associated to magnetic fields. Magnetic fields are going to collimate these powerful and beautiful jets, and therefore we know these are signs of magnetic fields in the early stages of evolution of a star. But magnetic fields not only affect the circumstellar environment of stars, they also affect the stars themselves. We know that magnetic fields are going to cause spots in stars, and it's been known for a long time that pre-main sequence stars, T Tauri stars, are variable, and part of this variability comes from a thermally inhomogeneous surface. Okay, so the goal of my thesis, I have 3 different goals. One of them is to understand what's the connection between the stars, their magnetic fields, and the circumstellar environment. I want to understand how magnetic fields affect the appearance or the surface of the stars. And finally, get an empirical correlation of this magnetic field strength and the internal structure of the stars. So to be able to do that, we have used iSHELL on IRTF. This is a high-resolution near-infrared spectrograph on the IRTF 3-meter telescope on Mauna Kea. This is a wonderful instrument. It's very new. It was commissioned and saw first light in 2016. I'm very proud to say I was one of the first few people observing with iSHELL, also one of the first few publishing paper with data from iSHELL. And I was recently reminded that I broke iSHELL one time, the first one to break iSHELL, but that was, I mean, it did break while I was observing, but this is one of the cases where there is a correlation, but not a causation. It just stopped working mysteriously that night. John Rayner recently published a paper with details, a lot of details about what iSHELL can achieve. So iSHELL is a cross-disperse spectrograph, which allows us to get a lot of bandwidth here. So this is one of the, this is a nice picture of what iSHELL can do. And for my thesis, I've been approved 350 hours of iSHELL time, and I have observed 164 individual sources. I've used the K-band, which is this portion there, the K2 in particular, from 2 to 2.3 microns. And the resolution I use in iSHELL is 50,000, although iSHELL can go up to 80,000. And some of the spectra, very nice spectra iSHELL can produce is shown here. This is a paper we published in 2019 with Mike, Bo, and Edwin, where we were observing many M-dwarf stars. And you can see the nice quality of the data we have obtained. Okay, one of the key aspects of going to the infrared for our study of young stars is that we can see the photospheric lines. So what I'm showing here is the spectrum of CY tau. This is a young source that we obtained with iSHELL. These lines I'm marking here in green correspond to photospheric lines. So these lines are from the star. These stars sometimes are behind massive disks and sometimes even behind many magnitudes of extinction and an envelope. So one of the nice aspects of going to infrared is that we can go beyond these many magnitudes of extinction, all this gas that is in front of the star forming regions, and we can actually see the central source. So we are not occulted by the disk or the envelopes. The fact that we can go to infrared is also very important since we can take advantage of the Zeeman effect. The Zeeman effect is what we use to measure magnetic fields. And put simply, it says that in an atomic transition, in the presence of a magnetic fields, energy levels are going to split. That splitting in energy levels is going to translate into a wavelength splitting, and that's what we call it Zeeman splitting. We see literally line splitting, like here I'm showing the solar case. In the part where there's no magnetic fields, a single line. And as soon as we move to part in where the magnetic field is very strong in the solar spots, the lines will literally split. The Zeeman effect depends on the magnetic field, but in terms of infrared, it goes as lambda squared with wavelength. That means that as we move to the infrared, we're going to be more sensitive to the magnetic field strength of the stars. So that's another great reason to use infrared observations in our survey. Okay, but it's not only just observing stars, then we need to actually calculate their stellar properties and magnetic fields in particular. And we have put together a method that combines different codes, the marked stellar atmospheric models, the Mux-Stowe radiative transfer code, and some atomic and molecular databases. And I don't think I can really go through everything I've done to develop this model. I've spent countless days and nights and years working on this modeling. We have published 2 papers on this method and applications in young stars. This code doesn't run in a laptop. We install it in a supercomputer, which we have to run for weeks to get the results. But I'm not gonna go into too many details. I don't wanna bore you with this. But if you have questions about this method, I am very happy to take them after my presentation is over. I can summarize very briefly what our code does. When we get a spectrum from iSHELL, then we feed it with this synthetic spectrum code, and we do it in an MCMC fashion and fitting many stellar parameters at the same time. We're going to use different lines, or the code takes different lines that are going to be sensitive, for example, to temperature. The different line ratios between the atomic transitions are going to be sensitive to the temperature of the star. Gravity can be calculated from the broadening of this line. So it's an indication of gravity. The rotational velocity of the stars also can be calculated from the broadening of the line. It's going to be a very particular signature. So faster stars are going to have broader spectral lines. And naturally, we're going to be using the Zeeman effect to measure the magnetic field strength. So the Zeeman effect is going to work exactly as I explained before. When the magnetic field strength of the stars is very small, it's going to be a single line. And when it increases here in blue, it's going to split the lines. That's how the code works for measuring the different stellar parameters, but it doesn't go one by one. It actually fits everything simultaneously and fitting all these lines. So I'm going to go into a little bit of more detail what I mean by young stars. So young stars, I'm going to be referring to class 1 sources. These are stars that are very embedded in their envelopes, in their birth material. They might have a disk and also outflows. Class 2 sources have already dissipated their envelope, so they're not as embedded, but they do have a large circumstellar material made of gas and dust. And class 3 sources, these are going to be stars that have already dissipated their circumstellar material, most of it at least. They might have a little bit of dust, which is likely not primordial. These stars are going to have different ages, going from less than 1 million years old to about 10 million years old for the class 2 sources, and then between 10 and 100 million years old for the class 3 stars. The classification of class 1, 2, and 3, it comes really from the spectral energy distribution. And more precisely, it's the slope between 2 and 20 microns. When it's positive, we call them class 1s. These are red line here. When the slope is negative, we call it class 2s. And when it's actually very, very negative without any contribution from the disk, it's going to be called a class 3 source. So I'm going to start with the class 2 sources and not with the class 1 sources. And the reason for that is that these are the only stars that have been studied before in terms of magnetic fields. These are very well researched, but also a great point for making a comparison with what can iSHELL perform versus what has been done in the past. So as I just mentioned, these stars are going to be in star-forming regions. These are going to have massive disks and going to have a negative slope in the SED. So what we know about their magnetic fields is that they're actually very strong. Here I'm showing the magnetic field strength in the y-axis in kilogauss as a function of the age in logarithm scale in the x-axis. This is a compilation of studies from Young et al. 2011. These are 31 sources compiled from 3 different studies by Hao Yang and Christopher Jones Krull in 3 different star-forming regions, and they measure a magnetic field strength of about 2.3 kilogauss on average. So we know T Tauri stars have actually very powerful magnetic field strength. These are as powerful over the whole surface as sunspots. So we have obtained our own observations of T Tauri stars by looking at stars in Taurus and Ophiuchus. And we observed 51 sources, and we derived physical parameters for 39 of them. So now we want to see how our parameters compare to what Hao Yang and Christopher Jones Krull did in the past. So on the left, I'm showing now the results that were published in a paper in 2021. And what we see is that, yes, the magnetic field strength in the class 2 sources we measure are very comparable to what was measured by Young et al. We do have more precise values here of the magnetic field strength and go from about 1 to 3 kilogauss, so very similar. And the average magnetic field strength we've detected in these 2 regions is also very comparable, 1.7 kilogauss. Now, our results are comparable, but I can tell you that they're more precise and reliable. And what do I mean by that? Is that iSHELL truly achieves it does a much better work when it comes to observing in the infrared. All spectrographs that were used for this study were only able to get the information of 3, 4, 5 different spectral lines, very small wavelength coverage, while iSHELL has a huge spectral coverage. This is what Hao Yang used to measure magnetic field strength in stars, and all that was actually contained in this part of iSHELL. So by using iSHELL, we not only have more access to lines in the photosphere of the stars, we have more information. And from that, we can measure stellar parameters simultaneously: temperature, gravity, magnetic field strength, and rotation. Now, because they were so limited in the information people was able to grasp from the infrared in the past, instead of fitting different parameters simultaneously, they were just adopting temperatures and rotational velocities from optical observations. What we're doing is different. We are obtaining simultaneously the temperatures and the gravities and the magnetic field strength of the stars. And that has led to a very important result. And that result is that the temperatures we measure for young stars are actually different when we measure in the optical and in the infrared. These are significantly different, and that's a very odd thing. For most stars, if you are getting the photospheric lines, it doesn't really matter what wavelength you're observing the star. But in young stars, it does. These temperature differences are actually very large. If we look at the temperature difference between optical and infrared in the y-axis as a function of the optical temperatures, we see that these are not small values. They are not 20 or 50 or 100 Kelvin that can be easily explained by maybe differences in the methods or the different observations. The differences we measure in T Tauri stars between optical and infrared go as high as 600 Kelvin. And for the most extreme case, which is T Tauri North, that paper we published in 2020, is almost 1,000 Kelvin difference. Now, these differences, as you can see, are not homogeneous. Not all stars are going to have the same temperature difference. These temperature differences actually increase toward hotter sources and also correlate weakly, but they correlate with the magnetic field strength of the stars. So there is a clear signature here that there is a correlation between magnetic fields and temperature differences. Now, the way we interpret these results is in the same fashion that we interpret the results of sunspots. In the sun, we know that magnetic fields are going to inhibit the convection in the outer layers of the sun, in the convective layers, and that's going to cause small but unconfined dark spots that are going to call sunspots. So the same is happening in these young stars. The only difference is that these stars have 1,000 times a stronger magnetic field compared to the sun. So that's going to create large spots on the surface. They're going to have spot coverages between 20 and 80%. And again, this is a magnetic phenomenon. And this is causing, and these temperature differences are causing ultimately the temperature differences we see. Okay, so one thing I wanted to get across right now is that the main way we classify stars is by knowing their temperature. So temperature is actually very important. At not knowing the temperature of a star, it really means that we are not going to know the masses of the star or the radius of the star. This is true for young stars because when we showed an HR diagram, a theoretical HR diagram with the gravity in the y-axis and the effective temperature in the x-axis, we see that young stars are going to contract through these vertical lines here in red that are mass tracks. They're going to start pretty high here and are going to descend, but they're going to descend isothermally. That means that if we know the temperature of a star, we're going to know its mass. The problem we're facing right now with T Tauri stars is that if we have two different temperatures, then, well, we should predict two different masses. But that doesn't make any sense. Stars only have one mass. Our problem is that we have two different temperatures and maybe none of them correspond to the effective temperature of the star. So how big of a difference does it make having optical versus infrared observations in terms of the masses of the stars? Well, the masses are going to be increasingly different as a function as we go to higher masses. And the differences can be up to a factor of 2. So these are huge differences when we're trying to deal with masses in low mass young stars. So the next point we tried to address in this paper was to know, okay, which of these temperatures is the one you should consider when we are looking at young stars. And we did that by selecting our sources to have ALMA dynamical masses. So they're going to have big disk around these stars. These are observations detected by ALMA of the Keplerian motion of the gaseous part of the disk. And this Keplerian motion tells us about what's the mass of the central source. So this is an completely independent way of measuring the mass of the star. And that's exactly what we need to test, whether optical or infrared observations is the one we should use. So we compare our observations in the following way. We obtain the masses based on the optical temperatures, and then we compare them to the real temperature, the real masses of the stars, which comes from the ALMA dynamical masses. And what we found is that optical derived masses, so masses derived from optical temperatures, actually differ quite a lot from the dynamical masses of the stars. The difference is about 40%, and there's definitely some structure there. Now, when we use our observations of infrared temperatures, these differences decreases a lot. So this means that the infrared observations at K-band should be preferred over optical observations when we're trying to derive masses of young stars. So infrared observations are going to be not only more accurate, but also more precise when we're trying to get masses of stars. Okay, so let's go back to our evolution of the magnetic field strength of stars. So I'm going to be populating this diagram where in the y-axis I have the magnetic field strength and in the x-axis is the age. So this is an evolution of magnetic fields. And we have completed here all the class 2 sources. So we shall now move to the even younger age, which is the class 1 sources. These stars are embedded and have not been studied very well. And part of that is because they're embedded and they can, for the most part, only be accessed at infrared wavelengths. And we know very little about their magnetic field strengths. So they're embedded, as is shown here. They have typically an envelope or maybe, and for sure a disk. They have different inclinations and the spectral distribution is going to be increasing. That means you have a lot of material around these stars. They're probably very buried inside the clouds. Now, before my dissertation, this is all we knew about magnetic fields in young stars. This is the only work known before my thesis started by Christopher John Skrull in 2009. This was done in collaboration to Greg Dopan. And then in 2019, we doubled the sample of class 1 sources, magnetic fields in class 1 sources. We made a huge improve, 100%. But we really wanted to go beyond that. So we surveyed many different star-forming regions, 4 in total. We went to the ONC, Serpens, but also Taurus and Ophiuchus that we mentioned before. We observed 53 of these sources, and we're able to derive stellar parameters for 35 of them. The sources were selected from Connolly and Green 2010 and also from Dobman 2005. So we went from this to that, where we have now a significant number of measurements of class 1 sources. And these are going to have a very strong values. So it seems that the magnetic field strength of class 1 is very similar to the magnetic field strength of the class 2 sources. And that has another implication, is that we can detect magnetic field strength very strong at ages of at least a few 100,000 years. Now, this address one of the fundamental questions we try to always answer in star formation, is how stars obtain their mass, how they accrete their mass. And we now know that it's not only the T Tauri stars that accrete their mass through a magnetosphere, but it's also these protostars. At least some of these protostars are going to be accreting accreting through a magnetosphere. Okay, so the other question we try to answer in this paper is whether there is a true evolutionary sequence between class 1 and class 2 sources. It's always been thought that this is an evolutionary class. It was defined like that. But what we really know about these stars in the classification is that one has more stuff around than the other one. One has more material, maybe it's behind a cloud, maybe it's more extincted. But this is only telling us about what the circumstellar material is doing and not what the inner source, the central star, is doing. And different effects, maybe the inclination of the disk or some orientation might be producing some confusion. So what we really want to do here, instead of looking at the circumstellar material, is looking at the star, at the central source. And we can do that by measuring the gravity of the stars. We know young stars contract as they evolve. They start very big and they start shrinking as they become older. Now, for that, it would be great to measure the gravity. And we have done that in this paper. We have measured gravities for the 35 sources, and I'm showing the distribution. And we see that the gravities measuring log G are going to go from 2.5 all the way to 4 in log G. And this more or less correspond to ages of about 0.1 million years old, or a few 100,000 years old, all the way to 5 million years old. And if we want to differentiate these from the class 2 sources, then we want to compare what they look like. So here in blue is the class 1 sources again, and the class 2 sources are represented in orange. These are the distributions of gravities. And what we see is that, yes, class 1 sources go to lower gravities, so bigger sources, and therefore earlier ages. But also there's an overlap between the class 2s and the class 1 sources. If we look at the HR diagram, we know they occupy some of them will occupy a different space than the class 2 sources, and while others there can be an overlap. Now, this means that there is actually a mixed group or a mixed bag of sources here. Some of the class 1 sources are going to be possibly true protostars with ages of less than 1 million years old, while other class 1 sources are just exactly as T Tauri stars in terms of their physical properties. There might be some geometrical effects, or maybe the time scales in which the circumstellar material dissipates that might be generating this confusion. But this is really addressing one of a very long-standing debate in the realm of star formation, of whether there is or not an evolution, and whether class 1 sources are truly younger. Well, I think we have nailed this now. And we know that, well, some of the class 1 sources are going to be much younger than T Tauri stars, while some others are going to be just exactly as T Tauri stars in the same age. That's what I mean. So, okay, let's go back one more time to this diagram. And we have now completed 2/3 of this diagram. We have the class 1 sources and the class 2 sources, and we see very strong magnetic fields for them. Now we're going to go to the class 3 sources. Okay, so these stars that have pretty much no gas around the stars. We observe class 3 sources from different young associations and co-moving groups. We went to TW Hydra, Beta Victoris, the Pleiades, and AB Dorados that have approximate ages between 15 and about 100 million years old. And we observed 40 of these stars and derived stellar parameters for 35 of them. Now, before I go into the magnetic field itself, I'm going to show you what the evolution looks like in an HR diagram. So here I'm showing how stars in the class 1 source, these are very big and they have very early ages. And as they evolve to the class 2 and 3 sources, yeah, they start shrinking, becoming more compact, and also lowering their gravities. Okay, so there's clearly an evolution between 1, 2, and 3s. We can see that also from their from a histogram of their gravities. There's a clear separation between the class 3s and the class 2 and class 1. There's overlap, but there's also some differentiation. Now, another thing I didn't touch much on was on the velocity of the stars. We know that, so we have measured that there's an evolution in terms of velocities, the rotational velocity of the stars, not motion, but actually rotation of the stars. And when we look at the histogram, we can see that class 1 sources, younger stars, tend to rotate much faster at the beginning. As they evolve, they're gonna rotate slower and slower until they get to the class 3 source. These are not exactly comparable to periods, because in the period there's also a radius term here, so not completely comparable. But this is telling us something about the evolution of the stars. It's the shrinking, it should cause spin up, but also magnetic fields are going to cause some spin down, because magnetic fields are going to couple to the winds of the star, and that's going to act as a brake. So we're finally in the position to tell, okay, what happens with the evolution of magnetic field strength. What happens with their, how do they evolve with age, and what happens with the internal structure of the stars. So here is the full sample of class 1, 2, and 3 sources. This sample has over 100 sources and spans pretty much 3 orders of magnitude in age. We can see that young stars are going to have very strong magnetic fields, and very surprisingly, maybe, these stars are going to keep their magnetic field strong for at least 100 million years old. This was not really well known when or if they're going to keep their magnetic field strength. And what we see, though, is that a few of these sources actually drop in their magnetic field. So there's some sort of difference here. Now, one way we can look at what's happening here is by not color coding the stars by their evolutionary class, but instead by their mass. So I have now taken each of these points, I put them in the HR diagram, use gravities and temperatures, and get the mass of the stars. And that's going to be shown now. Masses, stars that have masses of less than half a solar mass are going to be color coded in red. Stars that have masses between 0.5 and 0.9 solar masses are going to be in orange. And stars that are blue are the ones that have masses over 0.9 solar masses. So we pretty much got every single mass being for all the different ages. And what we can see is that it's only the more massive stars that are going to lose their magnetic field strength at an age of 100 million years old. We know, however, that those stars with similar masses, in this intermediate age part, the class 2 sources had powerful magnetic fields. So what's going on here? Well, there's one other way of looking at this is let's look at the temperature. So now we're going to be color coded by temperature. And we see that it's only the stars that are hotter than the ones that actually have a weak magnetic field after 100 million years old. So there's this differentiation, and this is really telling us something about the internal structure. So, okay, so only hot stars will, with ages of over 100 million years old, are going to show weak magnetic fields. So I'm going to show now the HR diagram one more time. These are from models by Faden 2016. And I'm going to show different lines. These lines mark the transition between fully convective stars to the right of this red line are going to be fully convective. And as soon as they cross this line, as they evolve and cross this line, they're going to develop a small radiative core. As they keep contracting, as they keep evolving, they're going to develop larger and larger radiative cores to the point when they cross this blue line, they're going to have radiative cores in excess of 65%. So if I plot now our data, this is what we see. I have color-coded the stars by their magnetic field strength. And if you stare enough at this picture, you're going to realize that there is actually no change whatsoever when star crosses this first red line. So the development of a small radiative core is not going to have any influence on the magnetic field strength of the star. Actually, when we cross the second line of 40% of convective core, it's also not going to have any influence. It's only when the lines cross the 65% line, at least 65%, that we see that stars are going to lose their magnetic field strength. So this means that the magnetic field, these powerful magnetic fields we measure in young stars, are pretty much powered by a small, thin convective layer on the surface of the stars. So if we go back to the this cartoon picture of what's happening, we know that young stars are gonna be born as fully convective, and as they evolve at the edges of T Tauri stars, they might develop a small radiative core, but their magnetic field keep being very strong, a few kilograms. They're gonna keep doing that up to an age of about 10 or 20 or 50 million years old, and same thing happens, no changes in the magnetic field strength. It's only at about an age of 100 million years old when the stars develop a large core that is going to significantly influence the magnetic field strength we see. So before I finish my talk, I'm going to just give you a little bit of insights into what's happening in terms of dynamo and raspy number. So in the solar paradigm of magnetic field generation, we know that there are two quantities that are important for generating magnetic field strength. One of them is the rotation of the star, differential rotation, and the other one is the convection of the outer layers. There is one parameter people use to encapsulate both of them that correspond to the raspy number, which is going to be the ratio between the period of the star, the rotation period, and the convective turnover time. Now, it's expected that as stars have stronger magnetic fields, they're going to have smaller raspy numbers, which is equivalent to say they're going to spin much faster. Faster spin should lead to stronger magnetic fields, and that's encapsulated by the raspy number. Now, however, we do not find any correlation between the magnetic field strength of the stars or this rotation over convection parameter, which means that the magnetic field strength in young stars are saturated. They're probably using so much, this spot so much of the photosphere that there's might not be room for more magnetic fields. So we have calculated the raspy numbers using Sommer's 2020 stellar evolutionary models. And what I'm showing here is the saturation of the magnetic fields. So in the y-axis, we have magnetic field strength, and raspy numbers here is in the y-axis. And there's not a clear evolution in the magnetic field strength here. Now, there's something that I definitely could not answer during my thesis, and something that it's very perturbing, but this has been for a very long time, is that if these stars, some of these stars are going to have the same internal structure, same velocity, same mass, same temperature, why do they have different magnetic fields? This is definitely not something I will be able to answer. Maybe it's somebody else thesis that's going to be addressing that. But some ideas might be that maybe there is it's the differential rotation what matters, or these stars goes through magnetic cycles similar to the one we see in the sun that could take years or even decades. So I'm going to go to my conclusion now, and the first of my one of the goals I had was to understand the connection between young stars, their magnetic fields, and their circumstellar environment. And we have confirmed that class 1 protostars with ages of only a few 100,000 years are going to have strong magnetosphere, and therefore they accrete through this magnetosphere. We also wanted to understand what can the magnetic fields do on the surface of the stars or the appearance. And we found that for T Tauri stars, they have large magnetically induced spots. These spots can cover 20 to 80% of the surface, very different from what we see in the sun. And this can cause these temperature differences we measure and are going to have deep implications of the masses and radius we calculate for stars. And finally, in terms of empirically connecting the magnetic fields to the internal structures, we have learned that the development of small radiative cores does not have an impact on the magnetic fields we measure, but once the outer layers thin enough, they have maybe less than 35% in depth, they're gonna completely destroy their dynamo, or they're gonna affect it significantly, so we cannot measure the magnetic fields. Of course, this is not the only thing I've done in my thesis. We have, for example, observed more than 160 young stars with iSHELL. This is excellent data that's going to be in the archive, in the IRSA archive, the IRTF archive. We have developed a method to measure magnetic field strength and temperature, gravities, rotational velocities, from which we have applied to over 100 sources. We have measured ages and masses for all of these too. We have conducted the largest magnetic field strength survey in low mass young stars using iSHELL data, and we have finished 5 papers, 4 of those which are already published, one that will be submitted in the next few days, and one more that is in preparation, which is the last chapter, the class 3 sources I showed you. So I would like to now give thanks to the people who has been supporting me. I'm gonna start with my wife, Karina, for everything you do for me, for traveling 10,000 kilometers and living with me here for 7 years, also for agreeing to move to Taiwan. So this is an interesting and lovely trip, for your love and support and all your help through all of this year. I would like to thank my family. This was a surprise, but my mom and my cousin came today. I was very pleased, and I really didn't know about it. So I wanted to say thank you, gracias mamá. También para la gente que me está viendo en Zoom. I would like to give some words to my family who might be watching this, maybe in YouTube later. So, gracias mamá, gracias prima, gracias por venir, por estar acá, por apoyarme, y también a mi familia por siempre incentivarme a hacer ciencia. I would like to thank Mike and Bo for being wonderful, wonderful advisors. I've enjoyed a lot this PhD. I'm always really happy to be working. Of course, sometimes it's hard, but I think this has been possibly the best 7 years of my life. And that's also thanks to you. I'm also very proud to say I'm Mike's first PhD student. I don't think I should keep that privilege, and I wish you, Mike, and many more students in the future. I would like to thank my thesis committee members, Greg Dobman, Sudong San, and Sasha, for all the input and help that they have provided over these years. I would like to thank IRTF team. I've been an IRTF student for many years now. I've been working closely with Adwin, with John, and I would like to thank them. I would like to thank Bobby Boss and also Charles, Mike, Thea, and all the TOs in Mauna Kea, and particularly at IRTF. Brian, Greg, Dave, Tony, and Greg Osterman. I would like to thank the IFA faculty for their support, for their help, for the classes they have taught. In particular, Jonathan Williams, who I did my 699 with, and probably the reason I am here in Hawaii. I would like to thank also Mark Chan for being a very awesome director here at IFA Hilo. I would like to thank everybody who make this possible. It's not only the faculties and the students, it's actually people running everything in the shadows in a way, or just actually the ones doing all the work. It's IFA personnel and secretaries Sandra, Amy, Pam, Mapuana, Susan, Evelyn, and also Bill, who's in Manoa. I would like to get the help. I would like to thank the help I've gotten from IT and tech support, Kurt, Raya, Rusheng, and George. Actually, Kurt deserves a lot of credit. He was the one that helped me to install this code in the supercomputer. I thank you very much, Kurt. I would like to thank all my classmates and all the students, Maisa, ZJ, Travis, Ben, Denise, Xiao, and Ja, and the IFA Hilo and Manoa students, in particular my 2 office mate, Erica and also Aldo. So with that, I'll now just leave my slide. Oh, yes. And yeah, I'll take questions now. Thank you.
Okay, so now it's time for questions and answer time. So I guess I'll start with the local audience, then go to Zoom land. So yes, Miles.
Christian, great talk. Thank you. I'm curious about the interplay between the accretion of the protoplanetary disk, for instance, and how that might affect, the angular momentum and the spin and rotation and the mass, and how that might all play into your magnetic field measurements and, moreover, the overall structure of the core star.
So the accretion, it definitely plays a role in the same way that magnetic fields create cold spots. The accretion events might create hotspots. So first, it should or might actually affect the temperature we measure in the stars. If the accretion is very strong, like XOR or FURI type of accretion, maybe over more than 10 to the -6 solar masses per year, you are actually putting a lot of matter and energy, and that will affect, for example, the external layer of the star. Stars might even inflate. There's some theories saying that if you have a lot of accretion, stars inflate. Maybe that's what we see in FURI type of objects. So it could affect gravities. Now we have not selected any star that is accreting too much to be concerned about that, but we are now running a campaign of observations of one star that Mike is observing with iSHELL, where this star is going through periodic bursts of accretion. It accretes so much that sometimes we don't see the photosphere. Everything starts to be in emission, the disk shines, and we would like to test using our model whether there are gravity changes. If the accretion is so strong that the photosphere is affected, you deposit so much energy that the outer part is gonna get bigger. But yeah, accretion should play a major role, and I don't think that's very well understood.
Interesting, thanks.
You're welcome.
Any other questions?
Very, very good talk. I'm just curious. I noticed that for each group of stars, you had the total number and then how many you had models. So there was always a fraction of, say, 10, 20 stars which were models. What was the reason? Was it that the data weren't good enough, or?
Yes, yeah, thank you for noticing that. The data we obtained was all actually really good. Different classes have different problems. The simplest problem was that when we observed class 3 sources and some class 2s, is that we realized those were unresolved binaries. So our code was not really, was not able to do a very good job with binaries. We didn't want it to contaminate having two different stars in the same spectrum and there get some weird parameters because of that. Now for class 2 and class 1 sources in particular, it's sometimes more problematic. Same as what Miles asked, these stars are going to be accreting. Some of them are going to be accreting too much and they change and they're variable. When we observed some of these stars, we realized that there were no photospheric lines. The accretion had increased so much that the disk was shining and all the lines we see it was completely like blanketed spectrum, no lines, or sometimes the lines went into emission. We had some of the class 1 sources that were rotating so fast and they had so much infrared emission from the disk that the lines were too short to actually derive accurate stellar parameters. So it's a combination of fast rotation, binaries in some cases, and the emission from the disk that in some instances prevented us from actually getting all the samples to be able to measure magnetic fields. I have the goal of produce a model that can fit simultaneously two stars in the spectrum. So we can actually deep blend binaries. That's a good thing we can do in the future. Observing binaries and getting their parameters is very important. It's not, for example, if they will affect each other, if the magnetic fields of close binaries are going to have any interaction. It might be predicted because in the main sequence, we have RS-scan band stars, these close detached binaries that have very powerful magnetic fields. So there might be some things that need to be learned. But for that, we need to first change the code and allow it to simultaneously measure the magnetic fields from binaries in the spectrum.
Well, great talk, Christian. You're certainly a star. But if my daughters were here, just to kind of put things on the ground level for some of us, does it have to get to class 3 to be able to see with the naked eye from the ground, or does that have nothing to do with it?
Yeah, so it's a good question. Actually, there is some connection. Most of the stars in the class 1 and class 2s are not only far away, a few hundred parsec away, but they are also, because they were just born, they are still embedded in the clouds that were born. So naked eye observations are really hard because our naked eye can see visible light. And these stars are going to be mostly observed with infrared. So we have been using infrared. The part that is not maybe so correlated is in terms of the classes, is that what we want to observe when we do naked eye observations are just close by and very hot and big stars. None of the stars I have selected are spectral type A or earlier, which is basically what we observe in the sun, in the sky, unless they're like super giants, which have completely evolved out of the main sequence. It's like dying suns, pretty much. But thank you.
Mhm.
Okay, so okay, one last question for here.
Great talk, Christian. Really, you built a very comprehensive, I think, story. So yeah, congratulations. I have a few questions, but I guess I'll just do one or two. Can you maybe explain a bit about the priors you were using on the MCMC? Because I'm curious that in particular, if the optical temperatures were not very reliable, what was that one of the priors, or how did you choose your priors? And do you have a sense of how the posteriors change after you select different priors?
Yeah, so the optical temperatures were not something we fit ourselves. The optical temperatures were mostly taken from the literature.
Correct.
And there's countless amount of information we take. So the only thing we measure is the infrared temperatures. For the most part, we didn't select too many different priors for the stars. We did allow them to vary in a large, for every parameter, we allow them to vary a huge range in set of parameters, and we run them. We do the two-step approach in which we allow them to somewhat converge and then restarting them again. We always check that they had converged before we published. And these temperature differences that I understand that it might be a bit maybe new, and it sometimes are hard to believe. Some of the temperature differences were observed not using our code. We use independent methods for measuring temperatures in the H and K bands, and we also saw these temperature differences.
Okay.
So yeah, and there's a recent paper by somebody else who sort of saw the same temperature differences, but they didn't really stress the importance.
Okay. And I guess one quick question.
Yeah.
The V's and I's are by construction lower limits, right?
Yeah.
So do you expect any kind of underestimation of the actual rotation, in terms of some selection bias that you're preferentially looking at stars that are axis on instead of, you know what I mean?
Yeah. No,
I assume that if you do with the infrared, you can see through the clouds, but I don't know.
yes, no, there's definitely something there. If the stars are even in the infrared, if you are seeing a star that is edge on, the disk is going to be so dense, like exactly edge on, that is going to be much fainter.
Okay.
iSHELL is mounted in a 3-meter telescope. Therefore, we have a very strong constraint on the magnitude of the stars. We only observe stars brighter than K magnitude of 11. And for those sources, we integrate often 3 hours on the star. So for stars that have edge on disk, for example, we have, for the most part, just omitted them completely, but in terms of selecting biphase.
Right.
And regarding V sin I, yeah, I think V sin I has this component of the inclination. So we might be looking at different, I mean, there might be some biases there, but more importantly, if they have inclinations that are very close to edge on, and they have lines that are too broad, that might also introduce some sort of problem, because if the lines are too broad and they're already very weak photospheric lines, then our code is just not going to work.
Yeah, I see. So the faster stars could be even faster, the ones that you measured.
Yeah, exactly. The ones we measure, one is 80 kilometers per second rotation. It might be faster. We don't. It's really hard to get inclinations. One way of doing that for some of the younger stars is looking at what the disk is doing. But at the same time, the disk sometimes doesn't correlate. The outer disk measured by ALMA doesn't always correlate with the spin of the star. Yeah.
Okay, so people in Zoom land, I guess you're welcome to unmute yourself and ask questions. We don't really see who you are, so please introduce yourself when you ask your question.
Hi, Kristen. This is John. Can you hear me?
Hi, John. Yes, I can.
Well, thanks for making IITF look good, and great suit as well. I hardly recognized you. Question: the error bars on the older, hotter stars are larger than many of the other error bars. Is that because the temperature width of those lines you measure?
So the last class, it's still a paper in preparation, the class 3 sources. I mean, what in particular do you mean? Is let me see.
Yeah, that one. Yes, those larger error bars on the older, and I guess they're hotter stars there. What's the why are those error bars larger?
So there actually, yeah, there's for that one is slightly simpler explanation, and this is a log plot. So
okay.
So they just appear to be much larger because just you have 100 Gauss plus minus 100 makes it look huge when you compare to the kilo Gauss plus minus 100. Sorry, this is just actually sort of a feature of plotting log. But yeah, that's thank you.
Okay.
Yeah, for hotter stars, lines are going to change. Some lines are going to disappear and others are going to appear. So yeah, we did account for that, and error bars should be, for the most part, fine.
Thank you.
Yep.
Okay. Any other questions from Zoom?
Yeah, this is Lynn Hillenbrand. Thank you very much for the opportunity to join. This is a great presentation, fantastic work. I wanted to understand from your presentation of the class 1, class 2, class 3, and the log G, log T plane. You had in particular a number of the class 1 sources were above the plotted theoretical tracks. And I was wondering what your thoughts were on that, if it was just our lack of understanding of where the maximum radius as a function of mass is, or translated into surface gravity, or if there's some systematic in the observations for the class 1s. And the one thing I could think of was that maybe you're measuring somewhere further out for the class 1s in the gas dust photosphere in the envelope, and not the true stellar photosphere. So I was wondering what your thoughts were on that.
Oh, thank you, Lynn. Yeah, that's a great question. So the models I use in that case are the Fading 2016 models. Those only start about 500,000 years old. I've recently tested a different set of evolutionary models that go all the way to 100,000 years, 0.1 million years old. All these are really hard to believe, of course. It's really hard to get really precise and accurate ages for these stars, especially from measurements like that. So I guess there's two things I want to say. When we tested our models, we did it on a combination of stars. We tested our method before starting measuring pre-main sequence stars. We measure main sequence stars and post-main sequence stars. So we measure stars with gravities going from 2 to about 5. And we think our method worked fine. So what we're measuring is probably the gravity of the stars. Now, maybe your questions also relate to what Miles mentioned here, that maybe some sort of accretion might be driving a little bit higher gravities than what we should be looking at. it's also entirely possible that these are truly younger stars. They occupy a very separate space in the HR diagram. And I would expect at least some of them to be real. There might be some more difficult one to achieve, but I didn't find by looking at the spectrum any particular problem. There is this new models, or somewhat new, by Edward Borg-Job, where they include accretion, and they see that the earliest stages of evolution, because of the accretion, stars are going to be jumping a little bit up and down in the HR diagram. So maybe all of these relates. I think what might be very valuable in the future is combining infrared and optical spectra, so and feed those two simultaneously. That will not only alleviate the problem with temperature, but might allow us to get a better grasp of gravity. So maybe it's a trade-off between getting the outer part of the photosphere and slightly inside of the photosphere. I'm not sure if that makes any sense.
Yeah, thank you. You've clearly given it a lot of thought. I've been watching your work for a number of years. It was nice to see it all in one place. So thank you again for the invitation.
Thank you so much. Thank you for attending today.
Okay, any more questions from Zoom? Okay, any more questions from here? If not, then we can end the question and answer session at this point. The audience here